All right, welcome to 3-2, working with polynomials. In 3-1, the investigation, we graphed a whole bunch of different types of polynomials and started to look for trends and different things that happened based on different factors that we had and different degrees and different roots and all that kind of stuff. So one thing I want to clarify is the difference between a factor and a root. So when I am in, this is factored form, because I have one factor times another factor times another factor. So each of these is a factor. So multiplied together, they all give me my y value. Now, if I'm looking for the x-intercepts, then my y value is 0, because everywhere on the x-axis, y equals 0. So for this, when I'm multiplying things together to equal 0, I'm going to use the zero product property. So each of these factors is going to have a root associated with it that I find by setting each part equal to 0. And in many cases, that's just doing the opposite. So x minus 3, the root is positive 3. But a lot of people don't quite understand that that's because I have x minus 3 equals 0, add 3 to both sides. Whoops. So x equals 3. Same thing with the 6 over here. Subtract 6 from both sides, so x equals negative 6. That's where the whole opposite thing comes in. It's whatever makes it 0. Now, something like 2x minus 5, people often make the mistake of assuming that x equals 5, which it doesn't. What we have to do here is add 5 to both sides, so 2x equals 5. Divide both sides by 2, and we get x equals 2.5. I'm putting it as 2.5 for the purposes of graphing. So each of these factors has a root that's associated with it. This factor, this root. This factor, this root. So it's important to know the difference between those two terms. So if I sketch, this is a third degree polynomial. And if I sketch this, and this is part of what we're going to be working on today, is how do you sketch these based just on the graph and not using Desmos or anything like that. I'm going to graph my x-intercepts at 3, at negative 6, and at 2.5. So this is going to be particularly difficult to graph because those are so close together. These are all just crossing roots, and we'll talk about how we know that in just a minute. Hopefully some of that you got from the investigation last time. Okay, we already know that part. So in this one, this is a table you need to put in your notes. Nope. So I'm not going to worry about the type for this part or the actual root for this part, and then I'm going to add in an example. Because if I have x minus c to the n, so starting from the top, what we can tell from the factored form of an equation, the x-intercepts. And what type they are. So if I have x minus c to the n, an example of that would be like x minus 2 to the, say, the third. The exponent doesn't really matter in determining what the root is because I'm looking for what makes that factor 0. So in this case, the number 2 would make that factor 0. So it's the opposite of what I have there, x minus 2. So the factor would be positive 2, or sorry, the root would be positive 2. So if I have over here, if I've got x minus c, then c is going to be my root. If I have x plus c, hey. All right, somebody popped in for a minute, so I got to start back where I was. The next one, if I have something like x plus 2 to the third power, I'm going to have a root at negative 2. So if I want to generalize that, my root's going to be at negative c. Now x to the n, if I just have an x or an x squared or x to the third or whatever, and there's no parentheses around it, that means that I have a root at 0. And that is the most commonly forgotten one. So the next part focuses on the degree of the polynomial. So if I have an even number degree, those result in bouncing roots. And you can see that on the investigation. If you have no exponent, or you have, sorry, this is for the degree of the term, not the polynomial. I misspoke. If you have no exponent, that's an exponent of 1, that results in a crossing root. And if it's an odd, not 1, it results in a flat root. So, for example, the root associated with x squared would be root at 0, and it would be a bounce because of the x squared. For the x minus 7 to the third, that would be a root at 7, and it would be a flat root because of the x to the third. And the root associated with x plus 4, that would be a root at -4, and that would just cross because that has first degree or just no exponent. If we know the degree of the polynomial, we know the maximum number of roots. For example, 4x to the second, so that's 1, 2. Parts of the 2 degrees, 3 degrees, 1 degree, so I have a total of 6 degrees, which means this is going to have no more than 6 roots. This particular one only has 3 roots because that is considered a double root. Whoops. That one's considered a triple root at 7, and that one's considered a single root at -4. All right. When we talk about the starting and ending direction, what A tells us is our orientation, which has all to do with the end direction. If the end direction is up, the orientation is positive. If the end direction is down, the orientation is negative. If A is positive, the end direction is up. If A is negative, the end direction is down. So if I'm even, they are both pointing in the same direction, and that is a positive orientation if A is positive. If A is negative, that flips. They both go down, and if I still have the even degree, and the orientation is negative. This is better with examples. So refer back to that 3-1. If my degree is odd, I have different arrows, but if A is positive, my end direction is still up, my orientation is positive. It's just now my start direction is pointing down. And then that flips if I still have an odd degree. If A is negative, end direction is down, start direction is pointing up. So the biggest thing is if A is negative, end direction is down. And if A goes positive, the end direction is up. It's all about the sign of the first term. Okay, so this one is going to have a positive orientation, and it's an even degree root, so you're going to have up and up. That gives us a negative orientation. That is even, So down and down. That gives us a positive orientation. And because that's in standard form, so that's our degree, our end direction is up, our start direction is down. That negative right there gives us a negative orientation, which means our end direction is down, our start direction is up. Okay. This was a group activity we did, and it was all about describing the graphs, but I just want to show you a couple of examples here. If I have a root at x equals -2, and it bounces, then my equation is going to be x plus 2 squared, or my factor, sorry, squared because it bounces, the plus 2 because it needs to be the opposite of that. My factor associated with the root at 3 is going to be x minus 3. That's just a crossing root, so I'm not going to put any exponent on it. And this is just y equals. My end direction is up, so I don't need to worry about making the orientation negative. Whereas if I have something like this one, my end direction is down, so I need to watch out for that. This root, -5, has a factor associated of x plus 5. Because it's a flat root, I'm going to cube it. This root right here, x minus 2 squared because it's a bouncing root. I'm going to make the whole thing negative because of the end direction, and there's my y equals. This one's going to have 4 factors because we have 4 crossing roots. So that one, x plus 4, no exponent. That one is just going to be x. That one, x minus 2, and x minus 6. Ending direction is up, so I don't need to worry about a negative. And finally, the factor associated with that root, x plus 3, it's bouncing, so it's going to be squared. X, crossing, so no exponent. And sorry, getting sloppy. X minus 4 squared. Ending direction is down, so I need to make that whole thing negative. And there's my basic equation. 3-3 deals with finding exact equations. This time, given an equation to graph, we start with what our roots are going to be. That one's going to have a root at 5. That's going to have a root at -3. So I'm going to put those on. I have a positive out here, so that means my ending direction is going to be up. This x minus 3 is a bouncing root. So what I know is when I come to 3, I have to bounce, go back up. I'm going to undo that. So bouncing root. So I'm going to come down because I know my ending direction is up. I'm going to bounce. I have to turn around to get back to cross down. And that's my sketch of my graph. This one, I'm going to have an x of -4, x of 1, x of 5. This one is going to bounce. This one will cross. This one will go flat. And I have a negative orientation. So when I sketch this, cross at 5, cross at 1, cross at -4. So since I know my end direction is down, I'm going to start from the end. At the x minus 5, that one's a bounce. 1 is a cross. That one is a flat. So I'm going to bounce here, turn around back up to cross. Whoops, that part was kind of ugly. Let's try that again. So bounce, come back up to cross, got to turn it around again, and then I have to make it go flat and go down. So that is working with polynomials based on what we did in 3-1. The next unit, or next section, 3-3, will be finding those exact equations. Thank you very much.